Hello, this is Richard Collins, your instructor in ATM 101, Weather and Climate of Alaska here at the University of Alaska, Fairbanks. Welcome to the first lecture of Unit 7, Water Vapor and Humidity. We start with a map of Alaska showing the annual precipitation. The precipitation represents the combined rainfall and snowfall over a year. The map shows the huge variation in precipitation across our state. In the southeast panhandle, there is about 335 inches of precipitation a year, with 226 inches recorded at Little Port Walter. As we move northward across the state, there is a general decrease in precipitation. In the Arctic, there is less than 6 inches of precipitation over the year, with 4 inches recorded at Kuparik. However, the pattern of precipitation is strongly influenced by geography. There is higher precipitation on the south side of the Chugach Mountains and the Alaska Range, and lower precipitation in the valleys on the north side of these mountains. There is also lower precipitation in the Tanana Valley and Yukon Flats than in the White Mountains and Brooks Range. In this unit, we begin our study of water and we explore its physical properties and its meteorology.
The overarching question that we're asking is, how does the cycling of water in the Earth-atmosphere system maintain a habitable planet? And also, what is the pattern of that habitability in terms of precipitation? There are several key themes. I list specific questions here, but the overarching ideas we'll be talking about are the meteorological behavior of water, the physical behavior of water as a molecule and as a gas, and how do we characterize water in the atmosphere, and how do we choose to characterize it that it makes sense meteorologically. The hydrological cycle is the cycle by which water moves through the Earth-atmosphere system. It's driven by evaporation over the ocean, which leads to cloud formation, then precipitation, rainfall on the land, and then runoff under the influence of gravity back to the ocean. It's a very efficient cycle. If the cycle were stopped, there would be 2 weeks of water supply available. So there's not a lot of water being stored in the system in any one place. It's moving very quickly through the system. And there's about an inch of precipitation in the atmosphere at any given time, constantly being resupplied by the large pumping effect of evaporation and the large return effect of water back to the ocean through gravity. Much of how we understand water and how it behaves in the atmosphere is based on the electronic structure of water. The water molecule is composed of 2 hydrogen atoms, H2, and 1 oxygen atom, O. Oxygen atoms are hungry for negative charge. Hydrogen atoms will give up negative charge, and so oxygen will try and hog the electrons of the hydrogen atoms such that on balance the oxygen atom stays slightly negative while the hydrogen atoms stay slightly positive. As a result, water molecules become sticky because the oxygen atom of one molecule will be attracted to the positively charged hydrogen atoms of another molecule, while the hydrogen atoms of one molecule will be attracted electrically to the negative charged oxygen atom of another molecule. This is demonstrated in ice, where water molecules come together in a very precise structure like Lego bricks to give us the crystalline structure of ice. And we see this in the formation of ice crystal clouds, that we have well-defined hexagonal structures that actually give us sundogs. It's worth noting that if we didn't have these electrical properties, the water molecule is light enough that it would exist as a gas at room temperature. It's these electrical properties and this stickiness of water that is why water exists as a solid, liquid, and gas in the Earth-atmosphere system. Water vapor exists in air. We think of this in terms of what happens when we have a liquid. When we have a liquid, we have a balance between the molecules escaping into the air, evaporating, and then recondensing into the liquid. And so we get a certain amount of vapor sitting over any liquid with a certain pressure. For that vapor, the vapor pressure. If we cover the liquid, like the beaker on the right, we will get to a point where the vapor is saturated, that the air is only holding so many water molecules in a balance between evaporation and condensation, and this is called the saturation vapor pressure. In the container on the left, as you know, if you leave a cup of water sitting in a room all day, it will eventually evaporate down to nothing because the water vapor will just be carried away into the larger room. But in the covered case, we get to a saturation point where we get very humid air sitting over the actual liquid. And we have this idea of a saturation vapor pressure, a maximum amount of vapor that can exist over a liquid at a given temperature. The temperature matters because the rate of evaporation is going to be driven by the temperature, and so the vapor pressure of the vapor over the liquid will depend on temperature. This capacity of air to hold water based on temperature is a very important effect in the atmosphere. The reason that cold air does not hold as much water as warm air is that as the air cools, the water molecules and all the molecules and atoms in the air lose their kinetic energy or have reduced kinetic energy, and therefore are moving at slower speeds, and therefore are more likely the water molecules to stick together when they collide because of their electrical stickiness. In warmer air, higher kinetic energies, higher speeds, the water molecules are more likely to ricochet and not stick together. Condensation is the act of water molecules sticking together and becoming large enough in droplets that they fall out of the air. The process is enhanced if the air is dirty, if we have what are called condensation nuclei, and in fact we see that in polluted air masses we get different rainfall formation than in clear air masses. But the takeaway fundamental message is cold air has a lower capacity to hold humidity than warm air. We quantify humidity by the mass of water vapor divided by the volume of air, absolute humidity. This is the classic definition of concentration from physics and chemistry, mass divided by volume, related to our concept of density, the amount of stuff in a given volume. We also can, in meteorology though, use specific humidity, which is the mass of water vapor to the total mass of air, the air plus the water, or we can use mixing ratio, the mass of water vapor to the mass of dry air. Why do we use these two, mixing ratio and specific humidity, in meteorology? Well, the reason is because in meteorology, as parcels move up and down in the atmosphere, they change their volumes. And so a parcel can change its absolute humidity while its specific humidity will stay constant. Well, from a meteorological perspective, we're not interested in the fact that the absolute humidity changed as the parcel moved in the atmosphere, because if no water fell out of the parcel, it doesn't matter that the absolute humidity changed. We're interested in the ability of the parcel to carry moisture and for it to travel in the atmosphere. And so in the meteorological perspective, there's nothing wrong with absolute humidity. It's just it doesn't fit the kind of processes that we're interested in describing in meteorology. A measurement of humidity in the atmosphere that is widely used is relative humidity, which is expressed as a percentage as the ratio of the vapor pressure to the saturation vapor pressure at any temperature multiplied by 100. If you want, it's the amount of water in the air relative to the amount of water that could be in the air if it was full of water. It's called relative humidity because, as we see, if we take two examples at 20 degrees Celsius and 10 degrees Celsius, the saturation vapor pressure changes. And so at 20 degrees Celsius, a given vapor pressure of 12.3 millibars equals a relative humidity of 53%. At 10 degrees Celsius, the same vapor pressure of water equals a relative humidity of 100%. And so you might say, well, whoop-de-doo. We now have a humidity measurement that isn't actually formally representative of the amount of water in the air. What it is, though, is it's very important meteorologically because we know that as the relative humidity moves to 100%, condensation must occur. So we can think of relative humidity as a likelihood of condensation to occur. For a given amount of water, we are less likely to have condensation at 20 degrees Celsius than we are at 10 degrees Celsius. As air cools, condensation is more likely to occur. We also highlight here that there's a subtle and small difference between the saturation vapor pressure of liquid over ice, and when we talk about cloud formation, this difference will make a difference in the formation of water droplets and ice crystals in clouds. So the takeaway message is at this point that relative humidity increases as temperatures decrease, and it gives us a likelihood of condensation occurring, which represents the transfer of water from water vapor in the air to water droplets that will appear as precipitation. The other thing about relative humidity is, as it varies with temperature, the relative humidity can vary through the day even if the absolute humidity doesn't. And it also explains why dew forms in the morning at the coldest part of the day when temperatures are at a minimum. The temperature that you have to get to have 100% relative humidity is called the dew point temperature, and the dew point temperature is an absolute measure of the amount of humidity present. While the relative humidity is not, the dew point is. It's the temperature you have to reduce the parcel to such that the vapor pressure is equal to the saturation vapor pressure. In measuring humidity, we use condensation in modern humidity measurements. In hygrow thermometers, we have a mirror that we chill until condensation occurs. We're bouncing a little infrared beam off that mirror. When the mirror clouds, the beam is obscured. The measurement device notes the obscuration of that beam and detects that cooling temperature as the dew point temperature. Sling psychrometers measure humidity differently. We have a wet bulb and a dry bulb thermometer side by side. The dry bulb thermometer measures the air temperature. The wet bulb thermometer will measure a lower temperature because the thermometer is giving up heat to the water that's evaporating from the wet bulb. If it's very humid, very little water evaporates, very little heat is taken from the thermometer, and the wet bulb thermometer and the dry bulb thermometer have similar temperatures, a small difference. As the air becomes drier, more water can evaporate into the air, taking more heat out of the wet bulb thermometer, and the wet bulb thermometer becomes significantly colder than the dry bulb thermometer, and the temperature is significantly different. And so the difference temperature between the two thermometers increases as the humidity of the air decreases. Satellites measure water vapor in the atmosphere using the infrared properties of water vapor. Water vapor is a greenhouse gas. It interacts very strongly with infrared radiation. It absorbs heat very effectively and re-radiates that heat very effectively. That's part of its nature as a greenhouse gas. Looking from space then, in infrared wavelengths, we see water vapor glowing very brightly, and here we see the patterns of water vapor over the North Pacific and Alaska, showing in white high water vapor concentrations, very moist air, and then in the darker regions low water vapor concentrations, very dry air. And here's an example of two satellite images taken in January showing the 7-hour difference between 5 p.m. and midnight in Alaska, where we can see how rivers of water vapor move through the atmosphere, and you can see the change in the water vapor concentrations over the coast of Alaska as the water vapor moves slightly inland over the 7-hour period. Vertical motion in the atmosphere is all about buoyancy. A parcel that is less dense than the air around it will rise. A parcel that is more dense than the air around it will fall. A warm parcel at the same pressure as the air around it occupies a larger volume and is less dense and therefore will rise. A parcel that is colder than the air around it is more dense than the air around it and it will fall. In the upper left diagram, where the air temperature increases with height, as in an inversion, if I take a parcel and I nudge it upwards in the air, it will become colder than the air around it, and therefore it has to fall back to the original position. This is called a stable situation. We return to our initial condition. Air does not mix vertically in an inversion. It stays local and is trapped. And this is the reason we get air quality issues when there are inversions, because if we're releasing pollutants at the Earth's surface, then they will stay trapped near the ground and reduce the air quality. In unstable air, the air temperature decreases rapidly with height, and so when a parcel now is nudged upward, it cools, but still remains warmer than the air around it, and so it can continue to rise. And in this situation, we get vertical mixing, and therefore, if we have smoke or pollutants being released at the ground, they will rise into the air and mix and disperse. And so it may be counterintuitive that unstable situations actually give us better air quality than stable situations. In terms of the profiles on the right, when we look at different environmental profiles of temperature with height, in A we have the temperature decreasing very rapidly with height, B and C also decreasing, D is an isothermal atmosphere, temperature is constant with height, and E is an inversion where the temperature increases with height. Whether the situation is stable or unstable depends on how those curves relate to the moist adiabatic lapse rate, when rising air, which is moist, will cool at 6 Kelvin per kilometer, or the dry adiabatic lapse rate, where dry air will cool at 10 Kelvin per kilometer, because as you remember, moist air is cooling, but there's also latent heat release when you're getting condensation, and so the cooling is less than when it's just dry air. In C, D, and E, any parcel that rises either has to follow the moist adiabatic lapse rate or the dry adiabatic lapse rate, and therefore cools faster than the ambient air and therefore cannot rise. Between C and B we have the moist adiabatic lapse rate. In this case, moist parcels can rise relative to B, but dry parcels cannot rise in condition B, because dry parcels will cool faster than the air is cooling in B. And finally, for A, all parcels, dry and moist, will rise because they will cool less quickly than the air profile A. And so A is unstable and is absolutely unstable. B is conditionally unstable based on humidity, and C, D, and E are all stable situations. We also look at the ability of parcels to move and what happens to their temperature as they move up and down in terms of Stuvey diagrams. There's a lot of information on a Stuvey chart, but I really just want to point out two important things. And that is that parcels that are moving that are dry will follow the red lines, and parcels that are moving that are moist and condensation is occurring will follow the blue dashed lines. And so if we look at the lower left panel, a parcel leaving the ground at 20 degrees Celsius or 293 Kelvin will go from A to B to C. It'll cool with height, and if it falls back down it will warm back along that track, and it will go back to A and B at the same temperature. A moist parcel looking in the upper panel will start at A and follow the blue, move parallel to the blue curves to B, cooling at 6 Kelvin per kilometer. And if it loses its moisture by the time it gets to B, and it now becomes a dry air parcel that rain occurred, then it will descend along the dry curves and it will warm at 10 degrees Kelvin per kilometer. And so the parcel will actually warm in going from A to C as it sheds its moisture. It will start as a humid parcel at A, rise, cooling, and then shedding its moisture through condensation, and arrive at C back down at the same altitude as a warmer parcel. This is how Chinook winds occur. Parcels rise over the southern side of the Alaska Range as air blows in from the Gulf of Alaska. They rise, they cool, they lose their moisture, and then they descend into the Tanana Valley, warming as dry air parcels, but now they're going to be warmer than they would be if the moisture had stayed with them, and so we get very warm winds in the middle of winter in Fairbanks, where our temperatures can jump from -30 to 0 or above in the course of a day. This question of lifting and cloud formation and rain is seen at all scales in the atmosphere. In a small convection cell, the cumulus clouds form in the updraft side of the cell, while clear skies form in the downdraft. The updraft, the air is cooling, in the downdraft, the air is warming, and that's why cumulus clouds initially when they form are so puffy and scattered. But it's also an issue of climate in terms of mountain ranges, as we discussed with the Chinook winds, that rain falls on the windward slope as air parcels rise over the mountains, and then On the leeward side of the mountains, it tends to be dry, and you can see this in the rain pattern of the Pacific Northwest, where as you cross the Cascade Range and then go into the Rockies, the westward sides of the mountains are moist, the eastward sides of the mountains are dry. That's a very marked climate difference across the state of Alaska for the same reason as we cross the Alaska Range. Again, going back to Washington and Oregon, the interior climate of Washington and Oregon is significantly different than the coastal climate for this reason. Just as it is in Alaska, the interior climate is incredibly different than the coastal climate divided by the Alaska Range. Closing thoughts and summary. The first thing, without reading all these, water is unique, and that uniqueness stems from the molecular structure of water. The atmosphere has a global water cycle. Water is constantly moving through the system. Water is a highly variable gas in the atmosphere because of its phase changes. We seek to quantify humidity in a variety of ways, but relative humidity is very useful in meteorology as it reflects the likelihood of condensation. Dew point temperature is also used because it's easily measured and it's an absolute measure of humidity. Water's infrared properties also make it easier to detect from satellites, and so the greenhouse properties we see of water also show up as remote sensing properties in water. Vertical motion is critical in the formation of clouds and the formation of severe weather and precipitation. And the stability of the atmosphere controls vertical motion, weather, and air quality, whether the atmosphere is stable or unstable based on how we get the temperature profile with height, either increasing with height, decreasing with height, affects what kind of vertical motion we get, and this plays out in terms of what kind of weather we get and what kind of air quality we get. In severe thunderstorm weather, we have a vertical profile that decreases rapidly with height, such that parcels can rise vigorously and at great speed into the atmosphere and form strong condensation, and that's how we get intense thunder cloud formation and intense storms. We'll talk about that more as we talk about precipitation later.